One of the ways of thinking about the derivative is that it indicates the rate of change of a function. Specifically, if a function f of t describes the amount f of a quantity that varies over time, then the derivative f prime of t describes the instantaneous rate of change of that quantity at the time t. This way of thinking enjoys useful applications in many areas of science. For example, in physics, suppose that the position of a particle is described by a function x of t, which varies in time t. Then, the instantaneous velocity of the particle is just the derivative of the position function. In other words, if v of t denotes the instantaneous velocity of the particle, then its value is just x prime of t at each time t. In addition, acceleration is by definition the rate of change of velocity, and so its value is obtained by taking yet another derivative. In other words, if a of t denotes the instantaneous acceleration, then its value is just v prime of t, or x double prime of t, that is, the second derivative of x. The acceleration describes how the velocity is changing with time. So, for example, if the acceleration is positive, then this means that the velocity is increasing. Whereas if the acceleration is negative, then this means that the velocity is decreasing. The velocity, on the other hand, describes how the position is changing with time. So if it's positive, then the position is increasing, but if it's negative, then the position is decreasing. All of these signs, positive or negative, are related to the indicated forward direction for the position function x. However, it's sometimes convenient to forget these signs and just talk about magnitudes. In fact, it's common just to talk about the speed of the object, which is, by definition, the magnitude or absolute value of velocity. For example, even though it's possible for the particle to have a velocity of minus 30 miles per hour relative to the forward direction of travel, such a velocity would determine a speed of just 30 miles per hour. As a quick example, let's compute the velocity, speed, and acceleration of a particle with position function x of t equals minus 16t squared plus 64t plus 96. By definition, the velocity is just the first derivative of the position function, which is given by minus 32t plus 64. Speed is the absolute value of the velocity, so it's just given by the absolute value of minus 32t plus 64. And acceleration is just the derivative of velocity, or the derivative of v of t, which is minus 32. In particular, this particle has constant negative acceleration, which means that the velocity of this particle is always becoming more negative at a constant rate. Another physical model that's important in the sciences is one of growth. Populations, prices, and amounts of substances all tend to either increase or decrease in size, and so it's often useful to model these quantities mathematically. Let's look at a specific example, the decay rate of a radioactive substance. The way a radioactive substance decays is on the level of atoms, whereby the nucleus of the atom loses energy by radiation. One of the physical principles of this decay asserts that the decay rate for a single atom does not change with time. Instead, for a single atom, the probability of decay is some constant, depending possibly on the type of atom that we're considering. What this all means is that if our substance consists of n number of atoms, then this decay rate is proportional to that number. That is, there is some constant k such that the rate of change n prime of t is equal to minus k times n of t. The equation we've written here is called a differential equation because it relates the derivative of a function, namely n, to itself. Notice, however, that this equation doesn't specify the function n itself. It just tells us how the derivative of n relates to n. Finding n is our job and something we can actually accomplish with math. Indeed, what we seek is a function n of t whose derivative almost equals itself but has an extra constant factor. Thinking carefully, we recognize that there's a function we know with exactly this property, namely the exponential function. In other words, we might guess that n of t takes the form of n of t equals b to the t for some base b. Now, Once we've made this guess, all we have to do is find the right constant b. Taking the derivative of this guess, we find that it's equal to n prime of t equals b to the t times the natural log of b. According to the decay rate equation, the constant that appears should be equal to minus k, so this means that we have that the natural log of b is equal to minus k. Now, it's possible to solve for b. We just raised both sides using e, and we obtain that b equals e to the minus k. Putting this back into our guess then, we obtain a solution of the differential equation. N of t equals e to the minus k, all raised to the power of t. In other words, n of t equals e to the minus kt. It turns out that this isn't the only solution though. Actually, any function of the form c times e to the minus kt will solve the differential equation, and the constant c just indicates the original amount of the substance at time t equals 0. Because indeed, when we plug in t equals 0 into this expression, we obtain c times 1. What this all means is that we can model the quantity of our radioactive substance by the function n of t equals c times e to the minus kt, where c is the amount of substance that we start with, and k is some physical constant describing the decay probability for a given atom.